from symbolic integration, which is what we've been doing. So we use the adjective numeric or numerical to distinguish from the symbolic integration we've done up until yesterday. So we promised you that we would tell you the formula, so maybe we'll build it up a little differently. So maybe we can think of it this way. Here's the idea. So the moral of yesterday. Approximating an integral using trapezoids seems sort of more efficient than rectangles. So why do I say that that was the moral of yesterday? Well, we did some examples yesterday. Namely, we studied a known integral, the integral of x squared. And we used that simple example because we knew its exact value, which is a third. And we did examples using a right Riemann sum, that's a rectangle. And then we said, well, maybe, and we saw that that wasn't very good at approximating. We had to use a lot of rectangles to even get 1 or 2 decimals of accuracy. And then we said, well, what if we used the midpoint of a rectangle instead of the right or the left end point? And then we realized, well, that could work, but that also requires us to do more calculation because we'd have to calculate midpoints. So then the idea was, well, maybe, and we're going to draw a picture here just to remind you, maybe if we have some function, so I'm not going to do x cubed, but I'll do some arbitrary function on AB. So if I have some function on some interval a comma b, so suppose this creature, I don't know, suppose it looks like this. So maybe this is our function y equals f of x. So let's just suppose, for the sake of an argument, I used 2 rectangles. And let's suppose I use the right endpoint. So here's my one rectangle. And here's my other rectangle. And the idea is that I have some air. Whereas if I were to use trapezoids, then we're wondering, can we reduce our air with, you know, and just by looking at this picture, it seems that we do. So this is kind of the point we want to make right now. Now, we did an example of this, and it's actually, not terribly difficult to derive the formula yourself, but in the essence of saving time, I will tell you what the formula is. But again, we derived it yesterday in the case of 4 trapezoids, and so you can easily do that yourself for any number of trapezoids. Does anybody have a question before we do that?
So you said that the midpoint is, it's like, it will give you an accurate, but the only thing is it does more calculation.
Well, we don't know that it'll be more accurate. It could be, at least intuitively. So the question was, what's wrong with the midpoint? And there's nothing wrong with the midpoint. It just requires you to calculate n extra points. Yeah, that's the one downside. And don't forget, the steeper your curve is, the more inefficient a rectangle is going to be because its top is flat. Whereas if a curve is steep, then using trapezoids eliminates a lot of that, either over or under estimations. Does that make sense? Okay, so here we go. What's the trapezoid rule? So the trapezoid rule says, I don't want to use this color. It says the following. And I don't want to write it down as a sum. I want to write it in summation notation. I want to write it as easy as for you to see the pattern. So, say that again. Go back. Yeah, sorry. Good? All right. So the trapezoid rule says that if I have an integral, and again, we assume that the integral exists, so like f is a continuous function, then we can approximate this in the following way. So this pattern is not, I wrote this down wrong, bear with me. Got the wrong indices. And so there's a pattern here that you have to be careful you don't mess it up. And that is every term inside of the sum has a 2 in front of it, except the first and the last. Now, why is there a 2 there? Well, actually, Shobit, that's the question you asked yesterday. Because if you go back to the previous page, whenever we compute the area of these 2 trapezoids, we're going to count this point twice right here. And so when we count you twice, we have to make sure we understand that we counted you twice. So since we're counting you twice, we have to accommodate that. So my advice to you is to go back to what we did yesterday when n was 4 and make sure the formula, you understand where it comes from. All right, so let's do a couple examples with this. It's actually pretty straightforward, and of course with a calculator it's even easier. So for the sake of having something to compare to, let's do an integral that is well known. To us. Let's integrate the integral from 1 to 2 of 1 over x dx. So let's use n equals 8 to approximate. So we know that this creature has a certain form. Now, here's what we need to do. I can't emphasize this enough. Before you do anything, you need to sort of get your puzzle pieces on the ground. So first off, what is your delta x? Your delta x is always b minus a over n. So in this particular problem, it's 2 minus 1 over 8, which is 1/8. You need that piece. And then what are your x sub k's? This is another thing that's difficult for us. Remember, it's always a plus k delta x. So in this particular problem, it's 1 plus k over 8. Now you can write this up cleanly. This is 8 plus k all over 8. So this is usually a step that students struggle with, and I hope that you take the time to understand what I did and ask a question if you're not sure. So let's make sure that it clicks with us. When k is 0, what do I get? 1, which is what I should get. Now what happens when k is 8? I get 16 over 8, which is 2, and that's what I should get. So then the pattern becomes, let's write it down again just for full clarity. It's delta x over 2. Then in this particular problem, it's going to be f of x sub 0 plus 2 times f evaluated at x sub 1 plus 2 times f evaluated at x sub 2 plus 2 times f evaluated at x sub 3 plus 2 times f evaluated at x sub 4 plus 2 times f evaluated at x sub 5 plus 2 times f evaluated at x sub 6, and then plus 2 times f evaluated at x sub 7, and then the last one does not have a 2 in front of it, and the first one does not have a 2 in front of it. Does anybody have a comment or a question? Now, let's write down the next step would be, okay, let's start plugging these things in. So this becomes 1/16 out front. And then x sub 0 is 1. So I need to plug 1 into my function. So that's 1 over 1, which is just 1. Then what's the next guy? The next guy is 2 times, what is x sub 1? Well, that's going to be 9/8. But when I invert it, it's 8/9. And then the next one is 2 times 10 over 8. But when I invert that, that's 8/10. And then it's plus 2 times. The next one would be, when I have 3, it'd be 11 over 8, or 8 over 11. And so then there's a clear pattern here. This is 2 times 8 over 12, and then plus 2 times 8 over 13. Why do I have to what? Well, what's the function? So the question was, why am I inverting these? Well, look at the function. It's 1 over. So that's a good point. So I should have maybe been a little more clear with that. Note the function here is f of x is 1 over x. So when I plug x of k in, I'm inverting it. So I have a couple more of these I have to do. Oh, change colors here. So this is 2 times 8 over 14, and then plus 2 times 8 over 15. And then lastly, you get a 1, and then it's just 8 over 16. That's the last guy. Now, of course, you can do all this in a calculator, and that's what I'm going to do. So I'm going to do that now. And then I'll show you. You can do this on Desmos real quick, and I'll show you that as well too. So if you plug this into a calculator, you get that this is 0.694122. So how much of this you do by hand versus how much you do using a calculator or computer is up to you. I typically wouldn't do this much by hand. I would probably go to Desmos and do something. So let me explain to you what I would do. So I'm going to share, and then let's go to the internet. Let's say I go to Desmos. So here's one way of doing this. You tell it what the function is. The function, as we know, is 1 divided by x, right? Now I got to tell it what my, so what do I want to do? I want to calculate, out front we know it's 1/16, right? And then what am I putting inside? Well, I know it's f of, what's my first point? It's f of 1. And then it's plus 2 times f of, well, what's the next one? The next one was 9/8. Plus 2 times f of 10/8. Plus 2 times f of 11/8. Plus 2 times f of 12/8. Plus 2 times f of 13/8. Plus 2 times f evaluated at 14/8. Plus 2 times f evaluated at 15/8. And then the last thing is plus f evaluated at 2. And then I close, and you'll see I get 0.69. Hopefully you can see that I got 0.69412, which is what I said on the previous page. Now, am I saying this is the most efficient way of doing it? No. But this is one way of doing it. You can also do it by hand. That's up to you. As I alluded to yesterday, the professional way to do it is to write code in the language of your choice that does it for you. Yes?
No, okay. Yesterday when we were doing the x squared, right?
Yeah?
And the first one we did from n equals to 4.
Yeah.
So outside we just kept 1, 4. Why not 1?
Say that again?
So out here, right?
Yeah.
We kept 1, 4. Why not 1 or 8? Or is it was
No, because we're using 4. But look at the formula. Okay, so the question was, here's the question, and I get what you're saying. So you're confused because yesterday I wrote the formula down differently. Remember, so yesterday I took this 1/2 and put it back in. So yesterday the first guy had a 1/2 and the last guy had a 1/2 and the ones in the middle didn't have anything. It's just 2 ways to write the same thing. Do you understand that? You sure? So here, let me illustrate again, because here was the question. The question was yesterday you had 1/4 out front. So, but I wrote the formula different yesterday. So here's what you need to note. Note, delta x over 2 times this f of x sub 0 plus 2 f of x sub 1, all the way up to 2 times f, let's say the 7th. Let's just say we're doing it for 8 here. This is the same thing as delta x times 1/2 of the first guy, plus, and then all the guys in the middle don't have any 2 in front of them. and then 1/2 in front of the last guy. So that's two ways to write the same thing. So what I did yesterday is I used this version, and what I did today is I used this version, but it's just they're equivalent. Does that make sense?
Just like to be more clear, right?
Say that again?
I just want to show you.
Yeah, come on. Maybe I did something wrong. I don't know.
Like over here, right? Why do you have the tools over here then?
Oh, because that's different. I'm using the actual formula. Okay, so here's where the confusion's coming in. Why? So the bigger question is why the 2's? So why the 2's in front of all terms except the first and the last? Or another way, let me say this another way. Maybe a better way of saying it is this. So you're going to say why, the question you have is why the 1/2 is another way of saying it. Why the 1/2 in front of the first and last? Well, just look at the case with 4. Look at the case with even just 2 trapezoids. So let's say this is the point. Say this is the point A, B, and now let's just say we're going to use 2 trapezoids. So we'll call this point x sub 1. So the area of the first one, what's the area of the first one? So you have, we'll call this A1 and A2. So A1 is equal to, well, what do we do? Remember how we did this. What was the area of a trapezoid? You take the height. So you take F evaluated at x sub 0 plus F evaluated at x sub 1 all over 2 times its width, which is delta x. And then A sub 2 is F evaluated at x sub 1 plus F evaluated at x sub 2 all over 2 times delta x. Now, notice that I have 2 copies of F of x sub 1, but I only have one of the others. So if I add these up, another way of writing this is, so maybe I'll go to the next page. So if I go to the next page, A sub 1 plus A sub 2 is, I'm going to pull the delta x out, and I'll pull the 1/2 out, right? So look, both these guys have a delta x over 2 in them, correct? So I'll pull that out. So what's left? What's left is an F evaluated at x sub 0, and then the first one has an F of x sub 1. Then the next one has an F of x sub 1, and then an F of x sub 2. So then I have 2 of these, and that's where the 2 comes from. Does that make sense? Right. So what we did when we did the example yesterday is we just wrote it like this. But when you're looking for a pattern so that you can have a formula, you want to try to write it as clean as possible. So that's why we write it as we did here. Does that make sense? All right. Any questions about this?
So that's the actual formula?
What's that?
Is that the actual formula?
This? Well, in the case where x is 2, yeah. This is the case. This is the case with x equal 2 trapezoids. The actual formula is this. This is for n trapezoids. So this formula uses n. And you can easily, if you draw it out, you'll see that they all going to get a 2 except the first and the last. Because the first and the last don't have any dancing partners. Everybody except the first and the last, everybody else is counted as the height of 2. So every point in the middle is going to be used for adjacent trapezoids. That's why it's counted twice. Okay. Very good. Now, again, we'll give you some of these to practice with. You know, watching me do it is not the answer. That's not how you learn. So the question you might also have, though, is the following. And that is, can we do better than trapezoids? And it turns out you can. We can use parabolas. Now, I am not going to go through all of this because the algebra is very, very tedious, but it's not a hard rule to follow, and it's called Simpson's rule. So it looks frightening, but here it is. It says that you can approximate an integral that's known to exist using the following rule. This time it's delta x divided by 3. So there's a 3 here this time, which is different. And then there's a pattern that is not the same as before, but somewhat. Here you alternate between 4 and 2. And this goes all the way till the last guy has to be a 4. And then the second to last guy is a 4, and the very last guy has nothing. And so there's one subtlety here for this pattern to make sense, is n must be even. So what we're going to do is this afternoon or this evening, I'm going to post an assignment, and then we'll do examples of these. It's scary looking, isn't it, Emily? That's all right. Don't stress about it. We'll do examples of this on Tuesday. Again, this looks scary, but it's actually, believe it or not, it's very easy to program a computer to do this. And then that's in fact what you do in the real world. And computers are real good at doing arithmetic. So we will do plenty of examples on Tuesday, but we got to give you something to try, and then you can ask questions. You have a question, Shobha?
So for this one, you keep on alternating between 4 and 2?
Correct, yep. So it's 4, 2, 4, 2. Now, the reason why this is the case is that you have to, if you approximate a curve with parabolas, you get this, there's a very simple formula for the integral, but you get all these duplicates because you're using points more than once. Anyhow, I'm not going to go through the derivation. It's way too much algebra. And you don't have to memorize it because you can always look it up if you need to use it. But you will need to know how to use it, is what I'm saying. All right, any other questions?
We will be drawing a graph and see how the formula comes about.
Say that again?
We will be drawing a graph and see how the formula comes about.
You can if you want. Yeah, make a table.
Yeah, then we will teach for like exactly.
Well, right, I'm not going to go through it for Simpson's rule, but you're more than welcome to look it up in the book or on Wikipedia. It's just too much algebra. It's not worth our time. We showed you how it works for a trapezoid. You can probably figure it out for Simpson's rule if you wanted.
But like, how does it look like? it was beautiful.
Yeah, so it looks like, it looks just as like you would imagine it. So Shobit asked, what's the graph look like? Well, here's the point. Take any curve, and let's pick your point, say x sub 7, x sub 8. Then pick any other point on this curve. We don't know what it is. The fact of the matter is I can always draw a parabola that goes through these 3 points. That's what you can do. And the idea is if x sub 7 and x sub 8 are close together, the parabola is going to be very close to the blue line curve. So you can read about it. The Wikipedia page is really good. You guys are, how do you hate on calculus? You guys, minus 40 for you guys in the chat today. Actually, minus 1,000. All right, guys, listen, I think this is a good place to stop. Don't stress about this. We'll do examples on Tuesday. I'll post some assignments. It'll all be good, all right? Have a good weekend. Thank you very much. I will be uploading an assignment soon. Ha, funny here. All right, guys, we'll talk to you next week. Have a good weekend. Thank you very much.